Hello, everybody. This is Bert Dixon presenting today on section 11.2 from our geometry text on similarity transformations, using similarity transformations to prove that two figures are similar. So if you have your textbook, go ahead and open to page 587. And you may recall from earlier in the year when we were learning about triangle congruence and just congruent figures in general, we said that two figures are congruent if there's a rigid motion that maps one figure to the other, or any combination of rigid motions. So rigid motions included things like reflections and translations and rotations. Those are transformations that didn't change the size or the shape of the figure. And so now that we're dealing with similarity, we're going to have another list of transformations that we can use to prove that figures are similar instead of congruent. So it includes all the same transformations that we did for congruence. It includes reflections and translations and rotations. But now that we're dealing with similar figures, it's okay to change the size as long as the proportions remain the same. And so we're adding on dilations. So the list of similarity transformations is the same as the list of rigid motions that we did earlier in the year, except we've added dilations. And so if there's any combination of reflections, translations, rotations, or dilations that map one figure to another, then we can say the figures are similar. Okay, so that's stated here. Two plane figures are similar if and only if one figure can be mapped to the other through one or more similarity transformations. Okay, so in example A here, to show that these two figures are similar, we can do a rotation. So this figure would rotate 180 degrees. So we see that point N rotates 180 degrees to point G, and point L rotates 180 degrees to point E, and so on. And so a rotation, we could actually even write the algebraic transformation. XY would get sent to negative x, negative y. And so, for example, this point, which is at 4, 1, got mapped to this point at negative 4, negative 1. And this point at 8, 4 got mapped to this point at negative 8, negative 4. And so we can do that with all the points to confirm. This is 4, 6, goes to negative 4, negative 6 down here. And this point at 2, 4 went to negative 2, negative 4. So all 4 points match this, which is a 180 degree rotation. Okay, and then for example B, we can see this looks like a reflection. And if we fold our paper, if you can actually fold the page in your book right along the y-axis, you'll see that this point lands on top of this one, this point lands on top of this one. You may remember the algebraic transformation that reflects across the y-axis. The x values change sign, but the y values stay the same. And so we can see that with every point. For example, this one at L is at negative 6, 2. It reflects to positive 6, 2. And we can do that with all of those points. So we can say, since A, B, C, D, E, F can be mapped to J, K, L, M, N, O using a reflection two figures are similar. Okay, and then go ahead and take a look at C and pause your video and see if you can come up with a similarity transformation that maps the small one to the big one, small triangle to the big triangle, or the big triangle to the small triangle. Either way will work. They actually do say in the directions to map RST to DEF. So go from the big one to the small one. Okay, so you may have recognized if we look at some coordinates like this is at 8, -2, and this corresponding point is at 4, -1, we see that all we're doing is cutting all the coordinates in half. So this is a dilation with a scale factor of 1/2. So that's going from the big one to the small one. If you wanted to start with the small one and go to the big one, then you would multiply by 2. So that would be a dilation with a scale factor of 2. It'll work either way to show that the figures are similar. Okay, going on to the next example at the bottom of the page. We're trying to decide if these figures are similar. And so to get from this point to this point, we're multiplying by 3. To get from this point to this point, we're multiplying by 3. And to get from this point to this point, we're multiplying by 3. So you'd say yes. The scale factor is equal to 3. And so that's a dilation. Okay, going on to 589, actually going on to 590. Go ahead and try problem 5. See if you can come up with a sequence of similarity transformations that will map CDEF to TUVF or vice versa. So these two figures are similar. You could use you could do this a couple of different ways. You could do a dilation with a scale factor of 2 centered at point F. So, or actually going from CDEF to the small one would be a dilation with a scale factor of 1/2. You see all these, the big figure has a side length. We're going down 4 and over 2. Going this way, down 4 and over 2, whereas for the small one we're going down 2 and over 1. So those are cut in half going horizontally. This is 1, 2, 3, 4, 5, 6, but on the small figure it's 1, 2, 3. And so all the dimensions have been cut in half. And the center of dilation would be right here at point F. That's the point that didn't move. So you'd say a dilation centered at F with a scale factor of 1/2. Another way to do it would be to start with the big one and multiply it. So do your scale factor, do your your dilation centered at the origin with a scale factor of 2, and that would move this point, which is at, right now it's at 3.2. If you do your scale factor of 1/2, then that puts it at 1.51. And so then your new figure is going to end up looking like this. And then you would just need to shift it right 1.5 and up 1. So that would take a dilation centered at the origin and then a translation right 1.5 and up 1. And that would work just as well. So there's different ways that you can accomplish the same thing. Okay, on the, at the top of page 591, this time looks like we might need a couple of transformations. They're giving us a hint here. You can map the triangle JKL to PQR with a reflection across the x-axis. So first, if I reflect it across the x-axis, it's going to end up down here. And then followed by a blank, followed by some kind of a rotation. And so we might want to do our dilation to get the sides correct. So we would multiply everything by, let's see, this length is 9 and this is 3. So we a dilation with a scale factor of 3, or we could say k equals 3. And so what that would do is it would move it. Too bad they didn't give us more grid space to work with, but that would make it the right size now. It would be like this when we multiply all the coordinates by 3. And then we would just need to do a rotation, a 90-degree counterclockwise rotation, and that would rotate it right up to where it belongs. So this point would rotate over to this point and so on. So that's a 90-degree counterclockwise rotation. Okay, and so now try problem F. Pause your video, try problem 8 on the bottom of 591, and press play when you're ready to check your answer. Okay, so again, there are various ways that you could accomplish this. You could start with your dilation first. So dilation with k equals, looks like 3 again, because this is 3 and this is only 1. And so it actually says start with PQRS, so we would need k to be 1/3. So if I do a scale dilation with a scale factor of 1/3, all the coordinates are going to be reduced by a factor of 1/3. So our figure is going to go here now when we multiply all the coordinates by 1/3. And then we just need to do a reflection across the y-axis. Okay, so that's one way to do that. The algebraic transformations would be xy gets sent to 1/3 x, 1/3 y, and then this would be xy gets sent to negative x, negative y. And then on page 592, note that all circles are similar. All circles have exactly the same shape. So if you start with a small circle, you can multiply it, you can dilate it by some constant, and it'll match the large circle exactly. So all circles are similar because you can use a simple dilation and a translation to map one circle to another. And that is it for today's lesson. Have a great day.